Welcome to our talk today. So first and foremost, I want to thank all of you for waking up nice and early with us. We think that you will take away some interesting nuggets, and it'll be worth the early morning wake up. So today we'll be discussing how Bridgewater Associates builds inspectable models at scale. And we will walk through exactly what inspectable models means and how we think about that at scale. Specifically, how Bridgewater thinks about the global economy, how they model that economy, and then how they inspect those models systematically using AWS technology. Now, this has been about a year-long journey together for this specific project, and there's a lot of challenges and interesting components that we've overcome, and we're very excited to tell you that story. So today with me is Laure, architect at Bridgewater, Robin, the director of research technology at Bridgewater, and myself, Anthony, senior solutions architect at AWS, working alongside Bridgewater. So without further ado, let me hand it off to Laure.
Thanks, Anthony. So we're going to tell you a story about one of our really hard problems and how we tackle that. And also part of the story is how we partnered with AWS to overcome some of the harder parts of this problem. We're going to start off with an overview of Bridgewater, what we do, what those problems look like. We're going to get into our architecture and how we solve some of those problems. And finally, we'll close looking back and seeing what did we accomplish and what are some best practices that got us to success. So let's start with what does Bridgewater do? What is Bridgewater? We are a renowned global macroeconomic investment firm. You probably know what Bridgewater is if you're here or watching this, but it's a very large firm. We manage well over $100 billion, and it's been around for a very long time in the space of investing. It's like over 45 years. Bridgewater takes seriously understanding fundamentally how does the economy work. And it's by focusing on just understanding how the economy works and evolving that model for over 45 years that we're able to last so long. We're focused on things that are timeless and universal. So we have timeless and universal economic and investment principles. What that means is when something is happening, we want to understand why it's happening, the root, like cause-effect relationship that leads to something happening. Let's take an example. You may have heard inflation is high. You probably notice this when you pay for things. You may have also heard the Fed is trying to do something about this by raising interest rates. So why would they raise interest rates? What does that do for inflation? Well, low interest rates promote borrowing. Borrowed money gets spent, and when you spend money, someone is getting that money, and so now they have more money to go spend. So spending grows. When spending outpaces the production of goods, prices go up, and that's inflation. So by raising the interest rates, you reduce the borrowing, you reduce the spending, and you dampen the effects of inflation. There are a bunch of great examples of these cause-effect relationships in this video, How the Economic Machine Works, by Ray Dalio, our founder. It's on YouTube. I highly recommend. It's just 30 minutes to just learn some of the basics of the economy. We take all of these cause-effect relationships and we research them, find new ones, just drive understanding of the economy and encode it into a literal model. It is our economic model of the global macro economy. This model runs continuously. It produces our portfolios, drives our trades at the end of the day. It's also used for research purposes. Imagine you had some expert on the economy and you could just ask a bunch of questions. Well, we have this model. They can ask a bunch of questions for that model. So it not only serves the day-to-day portfolios, it also serves research in the economy and in investing. Good models need to be inspectable and explainable. For Bridgewater, this is so important because a mistake can easily be worth well over $1 billion. We need to understand always what's happening, why is it happening. We need to constantly be evaluating our model, evaluating that it's doing the right thing, what are we missing. We need to ask questions. An economic model, the economy is extra hard. New data comes in every day, and it can be completely different from the past. The past does not predict the future. People are evolving. The economy is evolving. The world is evolving. So every day, new data flow in. The model is producing different behavior. We need to make sure, is it still right? If we want to trust this model, in our company to do investing, to do research, we need to constantly scrutinize it, make sure it's right. Use a new day of test cases. This is the problem that we're going to be focusing on today. This problem of validating continuously our model. But we simplify it a little bit. There's this big model of the macroeconomy, but we split it into mini models. Now, Robin is going to tell us about the architecture around those mini models.
Thank you, Laura. So before we talk about inspectable models, I want to give you a little bit of understanding of what our compute architecture is, because it's important for the story. For us, our compute architecture is entirely running on AWS. For us, new data is flowing in every day. This could be new prices, or this would be a new print for inflation. New data flows in, and we need to do what we call forward testing. Here we are taking the existing model, and we're testing against the new data. We also have to do back testing. That's when we take a model, make changes to the model, and we have to go check how would the model have behaved during the previous inflationary periods or previous recessions and things like that. We also have to model what we call these hypothetical scenarios. What if the war stops? What if the inflation continues? These are called what-if testing. And we also have to run these kind of simulations of our mini models. While we are doing all these research, we also every day have to produce trades in the market. We run in the markets every night. We produce these trades and throughout the day. AWS-based architecture enables us to scale out this process reliably. Now, let's take a 50,000-foot overview of what I call our computer architecture, and it's broken down into these three salient components. For us, a user here is an economic researcher. These are the people who are building these models, or mini models, as Laura mentioned. So a researcher would make changes to their model. It's in our proprietary platform and code. They would submit this to Amazon. Over in our compute grid, we have a compute driver and a build worker. The build worker will take the piece of code, compile it into executables that could run in our grid. The driver then proceeds to send the piece of binary over to our workers. We call the compute worker pods that would run in EMR on EKS, and it stores the intermediates on Amazon EFS. So very fast writes I/O is happening between the worker and EFS. The inputs and outputs are stored in our storage system. This is our data lake. So our data lake consists of three important components. First and foremost, all our data is stored in Amazon S3. The metadata for us is stored on top of Amazon DynamoDB. And finally, we use Amazon Elasticache for Redis to accelerate our read workflows. The final component for us is our reporting and analytics platform. We have a sequence or series of visualization and reporting tools that our researchers use every day. Today, I'm going to talk to you about introducing a new component to this architecture, which is the talk today, which is Amazon EMR Presto. This component we introduced to solve this inspectable model problem. And just remember this picture while we talk about the rest of the presentation here today. To give you some quick numbers about Bridgewater Research, our team, we store up over 20 petabytes of data, over 120 billion time series, and we run about 10,000 of these mini models executions a day. Now let's talk about how we build an inspectable models, and handing it over to Laura.
Thanks, Robin. So there's a very practical problem of how do you forward test? How do you do that inspection? Because we have this large, complex model. If you imagine validating a large, complex model, there are going to be a lot of validation issues. Issues happen. It's normal for there to be problems at some frequency. When these happen, someone needs to diagnose what went wrong. Is it something that we don't understand about the economy, like a gap in our understanding? Is it just a bug in the code? Happens. Or maybe it's some upstream data issue. Someone needs to look at that and understand why that's happening. Now, if you are a technologist, probably are, at AWS, you'll probably think about firing up a debugger. That's a great way of debugging problems because you get all the context of what are these variables set to, what's happening in this line of code, basically. We can't actually do that for our case. The model is too big. We can't stop trading. We need to keep the ship moving. But we still need to be able to debug the behavior of these mini-models. Operationally, we needed to make our models inspectable. So this is what we mean by inspectability. Without stopping, we can understand what the model is doing, ask all those questions that we walked through earlier. Let's go back to the example of inflation. Inflation is usually measured by a change in consumer price index. Now, there's a lot of economic jargon in here. You don't need to pay too much attention to that. But this is a very common model for inflation. In fact, you can find numbers for these on the US government website. This model, in this case, is a hierarchy. We add up numbers from the leaves, and you get the numbers basically towards the top. There's some hidden dimensions in this hierarchy. Like, we're not just dealing with USA. This is a global macro firm. So we also have the United Kingdom, China, Japan, Australia. We're looking at this across the world. We also look at it through time. The CPI today is not what it was a month ago. So it's a pretty large model that we're actually running through this. And people need to be able to ask questions like, what is driving the change in USA's total CPI? We have a system that'll answer that question for them. We call it provenance. Provenance will let you easily see that, oh, it was the oil-related fuel prices that led to some big change in USA's total CPI. Provenance is really powerful in helping people just understand why a value came to be the way it is. We implement provenance with a bunch of runtime instrumentation. We basically hijack the stack. We look at the traces of what's happening, what's being evaluated, so we can see, for example, in runtime that the total CPI depended on the core and non-core CPIs. We track all of this with runtime instrumentation, and we end up persisting that as like an output to S3, as Robin mentioned earlier. So all of our intermediate values, like what was the core CPI, which is in the middle of this hierarchy, get written out, as well as the traces, which look roughly like this tree. But as I mentioned, there are also hidden dimensions here, right? You also have a bunch of countries, you've got time, and this is a very simple mini model. The reality is we've got complex control flow, we've got like conditional branches, functional abstraction. So the models get quite complex, and it's really important to have the facility to capture the traces in those more complex control flow kinds of models. So to summarize, this inspectable model with our provenance system gives users transparency into any mini model. Anything in our entire system, someone can ask why, and they can get a good answer. This also helps offload the burden of always having to understand like how the system is working. You get the context. You're given the context in the answer to the question that you need. This again was implemented by persisting intermediates and traces. And ultimately, and all of this work is done right in model runtime. So now the analytics front end is able to take in this query that the user has and just look up the appropriate trace, get the corresponding intermediate values, and produce some good diagnostic information for them to use. This was hugely successful. This helps our investment research to ask questions of our model. It also helps operationally, because every day new data comes in, we need to evaluate the model. And this helps people ask those questions and understand what's happening and why.
Well, everything is great, right? Because it's a fantastic piece of tool. It allows us to inspect every model, right? things were really looking up for us. So we are running, imagine this, we are running 10,000 of these mini models daily. We're producing hundreds of terabytes of new data and traces. Each of these mini models are operating on millions of time series, billions of doubles or points. Now we can confidently operate all these mini models. That's great. So what happens in a company where we get confidence? Well, we build more, right? We build more mini models because now the operations teams can handle it, right? Because they are able to reliably operate these, right? Adoption goes up. And when adoption goes up, our economic researchers decide, hey, we could do more advanced things now because we can really understand what's going on. So our models get more sophisticated. So it's like a positive feedback cycle that goes on when we launch something like this, right? So new research products get unlocked, but there is a little bit of challenge here. One, if you notice, we are doing traces. There are a lot, so everything that we are storing is data times the complexity of the logic. As we increase the order of magnitude of data sizes, right, it has this multiplicative effect on top of the overall data that we are persisting. So these traces start to cause mini models to run slower. We knew that. But what happens is that, especially when we get into more complex research or more data-intensive research, right, suddenly things just don't work. And then as you operate these systems, as you look at the cost, you look at the storage, look at the compute, you suddenly realize these are doomed to skyrocket. So as I think, life is not so predictable because where you thought the success would lead you to versus where it'll actually end up is quite different. So we were spiraling into what I call a negative cycle. No engineering team wants to admit this, but it's true. Users start to become unhappy with performance, especially at these edges. Now, technology team, we are hitting scale-related incidents. As you know, running a production system, one thing or the edge is enough to kick out the system into a bad state, incident starts happening. And then leadership starts seeing increased AWS costs. So ultimately, we figured out, and this was obvious now, storing logic traces was just not going to work. Sorry, Laura.
Well, I'll try again then. So how did we really solve this problem? Looking back at that solution we had before, this was now the solution was 5 years ago, and so modern times call for modern solutions. But this solution from before was coupled with the model runtime, right? So that's why you have all of these consequences when you run the models, when you deal with all of the operations, all of the work is happening then. And as Robin mentioned, there's a multiplicative factor in terms of the complexity, the data times the logic is needed, both in terms of the runtime cost of having to produce all of these intermediates and traces, and in the storage, of having to store all those intermediates and traces. If you look at this tree, though, a lot of those lines are parallel. The relationships are very similar across a lot of countries. I mentioned in some cases we have control flow and stuff like that, so there will be complexities. But those complexities are really just about the logic itself, not the data. Is there a branching condition is just sort of one question of what's the predicate of that branching condition, rather than, no, just explode the branching condition, explode it to get all of these different traces for all of your countries. So we instead are thinking, all right, let's capture the logic. We can use static analysis, understand what the model is actually doing without having to run through it, without runtime instrumentation. We just look at the logic and understand the dependencies. Now, you still have to write out your outputs, so you still have the data leading to the scale of the model runtime. But logic now has this constant factor in terms of provenance. You only need to store this thing on the right, this sort of model logic itself. So this is a better encoding than this exploded out traces. This removes this burden from the model runtime, but now it adds some burden. Because we need to do some work on the analytics front end to actually answer questions. It's based on these traces. People need to see these traces. We need to recompute the trace at user waiting in the web browser time. And this is a really important thing to note. Whatever our solution is here, This whole provenance system is based on world-class economists and investors sitting there in front of a web browser. They hit a button, and they're waiting. And it is really painful when they have to wait for more than a few seconds, for sure. And if it's snappy, everyone is really happy. So we have another problem now of how do we actually get this query flow to work? So we hypothesize, all right, let's say we take that static provenance and the question the user gave, like what is driving USA's total CPI, combine that into a SQL query. That's a very simple model of abstraction. There are a whole bunch of query engines that exist that we can try to tackle this problem with to get snappy performance. And you could use the results of the SQL query to provide essentially those traces that were previously exploded out. But we don't have these solutions yet, right? Well, this is all hypothetical. We need to go solve this whole static analysis problem. We need to go figure out how are we going to get snappy performance in SQL. And the snappiness is a really tough problem because people are waiting, and waiting sucks. This led us to basic requirements for some query engine. If we needed to serve the user waiting in the web browser by going through this whole flow of combining the static provenance into SQL, running that SQL, getting the results back, and turning that into a trace, we cannot regress performance from the previous system. Yeah, it collapsed our operations, but users were happy when they could open their pages
That's right.
in the web. So we can't regress performance. We also need to support UDFs. We have a custom time series data format. We need to run functions on those in order to present information to the users. We store our data in ORC format in S3, so we should be able to do that. Finally, there's softer requirements we landed on, like we want SQL compliance because, as mentioned earlier, I don't want to hedge all of our bets in some particular solution. I want to have some agnosticism, have some ability to sort of switch things out. If something isn't working, we can use another solution. SQL is a great intermediate for trying a bunch of off-the-shelf query engines. Finally, we also wanted this soft requirement of flexibility for caching because we know you're not going to, there's a magic physics problem here of actually crunching the numbers well enough. You're probably going to need caching. You're probably not going to be able to just depend on all of the work happening every time someone loads a page. So we want some flexibility in case we need to pull those levers. And we don't want to manage our own servers, so EMR is the name of the game. Amazon EMR. So as we gathered those requirements, we reached out for this whole re-architecture. We reached out to AWS to set up a data lab. And we worked with the data lab, collaborated, looked through a bunch of options that we had, and evaluated them against our problem. So first, we looked at Redshift. Redshift, we found that the initial load would be too slow because you're moving a lot of data into the whole Redshift basic database. And we looked at Amazon Athena. This one seemed really promising. But there was one critical piece that was slowing us down, which was the UDFs needed to move across the network to run on Lambdas, or the data needed for the UDFs, because the UDFs are in Lambdas. So we looked again. Apache Spark is another option. There's some overhead in setting up your Spark cluster. And so we were worried it wouldn't be snappy enough in order to get good isolation around our data, too. So after lots of back and forth, and I actually should caveat, all of these could be made to work. There isn't an off-the-shelf thing that just magically answers all of our problems, but with engineering work, you can make these things. You can make these things solve our problem. But we ended up landing on Presto on Amazon EMR. This one seemed like it would be the easiest to actually get running and solve our problems. The UDFs are executed in process, right there with the data. There's direct integration with Amazon S3. And I guess we heard recently about the zero ETL for Redshift, but at the time that didn't exist. And a whole bunch of caching options. It's fairly mature Presto. We also ended up needing a data catalog for Presto. We chose AWS Glue. There were a bunch of decisions in there that we won't need to get into here. Now let's look at the architecture for this new case, this new system that we have. There's the analytics front end that Robin mentioned, and this new query engine, all backed by storage in S3. So it starts with the user's query. what's driving the change in USA's total CPI. The analytics front end takes that query and sends it to a query service, which will produce SQL queries that we end up running on underlying data. We send those off to Presto, and those will get our data from S3, bring it all back, produce those traces for the analytics front end and for the user. Presto worked really well, but it had some challenges. First of all, the default configuration wasn't right for us. Thankfully, we had a bunch of experts from Amazon help us work through what is a good configuration for our case. We also found that AWS Glue became our primary bottleneck. And in fact, Presto has its own caching to deal with this, and we ended up needing to do our own solution to deal with this as well on our side of things. So we added an Elasticache for the metadata. There are also some kinds of questions that we know users are going to ask. And we need them to be snappy because they're so common that people ask these kinds of questions. So we offload some pre-work into a dedicated batch cluster. Batch like it's running with the model runtime, but sort of asynchronously, fire and forget kind of thing, so that we can make sure that those common cases are still snappy. Now let's step back to the overall query flow and look where we came before versus after. Previously, we exploded out all of these traces. We had the model runtime collect these traces and persist them to S3. This scaled with data times the logic. Our new approach, which is effectively data plus the logic, at least for the provenance features specifically, involves just analyze the logic, have a static model of that source code, essentially, project the query through that into SQL, and run that query to produce your traces. This is a pretty awesome change. It cleaned up so much from our model runtime. These traces are now calculated on demand in Presto instead of burdening the batch runs, the operational concern runs. So we just eliminated explosive growth. Now when they run their models, run their mini models, they have way reduced runtime because they don't need to do all of this producing the traces and persisting them and the intermediates. And it's still snappy when people want to inspect in the analytics front end. We can also forget about this problem. We had a big bottleneck here, and we've got bottlenecks all over the place, but this was really the one that was a problem, and now we can forget about it. It also opened up some new doors. We can optimize the SQL queries so that when people actually get the results back in the analytics front end, it's faster. We can even better optimize the runtime itself because it was kind of constrained by all this runtime instrumentation, and we can simplify a lot of the actual runtime environment for the mini models. And there are a bunch of new features that, like if you actually have SQL backing the thing, like sorting and limiting, it's just like basically one line in SQL. So that's super easy to actually add that feature. We have linear scale for inspectable models using Presto on EMR. This also gave us a benefit of forgetting about the scale problem. It's Amazon's responsibility, essentially. So we can just scale up our Presto cluster as we need to meet more demand. And any new features they have, we can just take advantage of. So this inspectable model of the economy. As Robin mentioned, for the first time around, again, the second time around, we have a recipe for success. There's new research happening, new features and greater scale from our platform. We've done some decoupling, and that enables both the research teams and the engineering teams to just focus on their problems and not have to deal so much with the constraints by that coupled provenance system from the past. Also, this is a performance improvement. Performance improvements don't stop. We're going to continue to do more performance improvements. We're working on a bunch of things right now, and new requests come in for new features. But this is part of putting the pebble in the right shoe, which is key to having an architecture for the future. Just like make this scale problem more of a standard industry problem, not some weird in-house kind of mess that we built. Now, Anthony will walk us through the impact of our architecture.
Thank you, Laura. All right, so we went through the initial problem, how we thought we solved that problem, how there was still a problem, and then how we actually solved that problem once and for all. I want to spend some time with everyone on the impacts. What was the end result from both a technology perspective as well as a business perspective? So just a quick reminder that we moved, so from a technology perspective, we moved runtime from the producer to the consumer. And what this means essentially is that we're able to do just-in-time inspection when the query actually happens. We've decoupled the producer from the consumer. And what that results in is not having to spin this up all the time and having a fraction of the cost per inspection when compared to the previous architecture. Next, as we mentioned, models are written by economists and researchers. And so we're really intentional about decoupling the roles and responsibilities. We have researchers and economists asking questions, writing queries, and we have the engineers actually working and building on and improving upon the provenance system. Now, this decoupling allowed for that, and it also allows for low-level optimization to be done in real time, in production, without ever affecting the researchers. They really don't even notice. They don't notice the cost improvements, the performance improvements. They happen continuously. Next, we mentioned that we've decoupled this architecture, and this decoupled architecture fits nicely into Bridgewater's larger microservice strategy. And so it's part of this larger decoupled architecture from a storage and compute perspective across the organization. Next, we are better utilizing our infrastructure. So specifically within those mini models, the CPU utilization is much more efficient now that we're able to independently scale the consumer as well as the producer. And all of this results in larger models, more complex models, but now in linear runtime, which enables that at-scale component that we started the talk with. So one last time, I just want to show you all the overall architecture. Now, this talk, as you remember, focused on one component, but this is sort of the larger architecture in how it interfaces with the storage, as well as the HPC grid on the left-hand side there. OK, so we've touched on the technology impacts a bit. What are the business impacts? So in a few words, faster, cheaper, and smarter. We saw a 2x reduction in average job runtime. And this translates to, on average, a job taking half as long as it used to. That inspection that we talked about. Now, this is a result of decoupling and independently scaling jobs from the storage layer and the compute layer. Second, we're more utilized. So we see an over 75% machine utilization across the architecture. And this removes the bottleneck of capacity, and it enables components to scale independently. And then finally, we saw a 5x peak job increase. This means at peak, we can run 5 times the number of jobs than we could previously. This was unthinkable beforehand. And once again, these business impacts translate to one simple outcome: researchers and economists being able to ask more interesting and complex questions in a performant manner. OK, so looking back, we've come a long way in our journey together. And we've touched on performance and cost, but I want to touch a bit on resiliency. So as I mentioned, the decoupled architecture, we were really intentional about building something that is simple to understand and easy to optimize. So we've explained this architecture roughly at a high level in about an hour. And that enables us to sort of unlock resiliency by modulating different components. Second, we focused on using AWS managed services. This enables Bridgewater to focus on actually building the provenance system and not worrying about infrastructure. This also helps with resiliency across availability zones and regions as well. So bad days happen to all of us in technology, and we've designed this to help on those bad days. So as we mentioned, the storage and compute scale independently, and so we're able to have multi-AZ as well as multi-region like designs for this architecture to enable resiliency. But we are also, or rather Bridgewater was also able to build what they call a turbo button. Now this turbo button, if you remember that 5x peak, enables them to sort of press a button and scale up this infrastructure essentially 5x. And that enables us to catch up if there's some sort of event, or if researchers and economists are asking a lot of questions on a potentially busy market day, we're able to meet that demand. And so all of this resulted in an 80% reduction in total downtime in 2022 versus 2021. Now for cost. So the impact of cost was pretty profound here as well. If you look on the right-hand side, we see a graph that essentially tells us that if you remember the 20 petabyte data lake, that has grown year over year about 42%. However, cost of that data has actually gone down 35%. And this would be sort of impossible if we didn't have a decoupled architecture. Now, it was enabled by S3 intelligent tiering. No engineering effort essentially required. It was a few small configuration changes within the provenance system, and it was completed in a matter of days. On the compute side, from a cost perspective, we see that we're running about 20% more jobs year over year at exactly the same cost. Again, this is a bit a result of the decoupling, as well as the managed services, as well as the increased utilization that we see for the machines. Okay, so before I hand it back to Robin to close us off, I want to quickly touch on some lessons that we learned. Number one, security. So we didn't talk a lot about security in the talk today, but security is core to all the designs that we complete together with Bridgewater. And specifically, this modular approach enabled us to perform security reviews at each module rather than waiting to the end of the project. This really sped things up for us. Next, iteration. So we created frequent, smaller, less finalized versions pretty quickly throughout this year to test and then fix the things that weren't right in a pretty quick manner. And I want to thank both Laura and Robin for their leadership in the iteration respect, because it really led to a lot of innovation in a pretty quick 12 months. Next, long-term design. So we're working backwards from sort of an ideal solution that we talked about. There's never a perfect solution, but we do have a North Star of the critical components that we're working towards. In order to balance the long-term ideal solution, which really doesn't exist in practicality, we design from first principles. Now, what that means in reality is that we sat down together really early on in a room, and we worked through the functional, non-functional, and the business requirements so that we understood what was critical and what was not critical. And this made the sort of designing process a lot easier when we came to Crossroads throughout the 12 months. So in that, I just want to thank the whole Bridgewater team for your partnership. It's been a lot of fun, and I'll hand it over to Robin to close us off.
So thank you, Anthony. This was a very fulfilling project for us. And one of the things that we did very differently compared to previous projects with AWS was a structured process. We started with the roadmap planning, which is about a year ago, or 18 months ago, when you said, hey, we want to build the system, right? We want to move to this architecture. Here are some guiding principles. Here's a North Star. Really lay that out. Then we started doing architecture reviews. Throw some designs up there, make it clean, make it understandable, make sure everybody understands, both from the Bridgewater side and the AWS side. Then we started doing executive alignment, make sure that the leaders from both sides are making sure that they are in for this project. Then I loved these AWS data labs, really smart, right? Really smart, insightful, like highly skilled engineers and architects coming in, really looking at the problem, finding creative solutions to it, trying different ideas. Like we went through the whole gamut there, right? Like we Redshift or Spark and UDFs and trying to find out challenges with them. And what happens with that approach is because we get enriched with a good architecture on our side, and AWS gets enriched with insights into what to optimize and get inspiration on real customer use cases. And finally, once we built the project and launched it, there was a lot of optimization exercises, starting with trying to figure out what's the best way to run Presto clusters. What is the best way to like use Glue, use that backing with S3 or use back with Aurora, use caching in the mixture, try to figure out how to do a batch cluster and a real-time cluster, and how to make sure that the catalog talks to each other, how to make sure it's multi-region, it's resilient, right? Try some exercises to knock things off and see what fails, right? So a lot of like engineering effort went into just making sure that it is ready for prime time. So this process, I think, helped us a lot in this project, and I really want to thank AWS team for that. For us, when you look back at it, we have this provenance system. I think it's a pretty unique way of running data models at scale, right? Running explainable and inspectable data models at scale, because we need that, because we run business processes. We have these questions, and to have a system that keeps up with the business is a great, great thing. So thank you all. Thank you for attending this talk today, and thank you, Anthony. Thank you, Laura.
Thanks, guys.
Thank you.